Hello, everyone, and thank you for joining. We're excited about our continued partnership with EasyTech MegaChips and the opportunity to bring this technology to you. I'm Mike McKenna from Engenuity Systems, and I wanted to give you a little bit of background about Engenuity before we get started. We were founded in 1994 to focus on the development and design of LawnWorks interface cards, I/O devices, and drivers. In the late 90s and early 2000s, we were one of the leading LawnWorks experts, but we began noticing a shift in the market to include more open system protocol and a drastic increase in the types of industries that were applying the technology. Since then, Engenuity has added Master Niagara AX and NFORD certified engineers, technicians well-versed in IoT, open API cloud solutions, system design and pre-programming services, and one of the fastest growing UL panel shops in the country. We provide a wide range of manufacturers representing all of the major protocols and over 60,000 products to meet your solution needs. Engenuity has products to over 80 countries, providing global solutions to companies of all sizes, from one-man shops to Fortune 100 companies. We have the resources and know-how to add value to your business. If you have any questions during this presentation, please feel free to raise your hand or type it into the question box. And at the end, we'll have some time to address those. Now I'm pleased to turn it over to Michael Navid at MegaChips to start the presentation on the HDPLC technology. Go ahead, Michael.
Thank you, Mike. Hello, everyone, and welcome to our webinar today. My name is Michael Navid from MegaChips. Today, we're going to talk about how to build faster networks for smart city and smart building applications using LAN. Over the last few years, we've seen a dramatic increase in the bandwidth demanded by modern applications. More nodes, bigger packets, more security. All of these things increase the amount of data traffic in industrial networks. Legacy communication technologies like RS-485 or narrowband power line communication struggle to meet the new requirements for industrial networks. Yet, for a lot of installations, it's not practical to install new wiring infrastructure like Ethernet. So what do? Today, we like to propose another option, a high-speed power line technology called HDPLC that's developed specifically for the industrial networks, including smart buildings, smart lighting, and many others. I'll be talking about the new requirements demanded by customers in the industrial IoT space and how we're addressing it with HDPLC. Then Matthias from EasyTech will talk about its applications, its implementation in real-world scenarios, and the products they have in the pipeline based on HDPLC. But let me start by introducing myself. I've been working in the high-tech sector for the past 30 years, mostly in semiconductors. I've been involved in power line communication for more than a decade, working with various industry organizations, standard bodies, system integrators, and other key players to advance the power line communication technology. I've been with MegaChips for the past 4 years, helping them enter this massive IIoT market. I believe PLC is the next step in industrial IoT communication, and it's critical to its success. I've been involved in various PLC standards at one time or another, from HomePlug to G.HN to G3PLC to HDPLC. Today, I'm applying my experience and energy to bringing the benefits of broadband technology to smart cities and smart buildings worldwide, which is the subject of the webinar today. Just a little about MegaChips. We are a Japanese fabless semiconductor company founded back in 1990 with headquarters in Osaka, Japan, and San Jose, California. We have a global reach with offices, R&D centers, distributors, and partners all over the world. Our revenues are about $800 million a year, and we have about 900 employees worldwide. We have a wide breadth of technologies and products, and we service a wide market area from consumer to industrial IoT. As you can see, most of our revenue comes from our ASIC and custom ASIC business, and that's how the company was founded more than 20 years ago. but we have kept the same culture and mentality of a custom ASIC design house and pride ourselves in providing the best customer service and support to our customers. Contact us if you ever have a need for a custom ASIC. Otherwise, our standard products are available through our website and through our worldwide distribution channels and sales offices and partners. So let me start by trying to explain the challenges facing system integrators and the IoT industry in general when it comes to data communications. With the explosion of IoT devices forecasted in the coming years, and as the networks get bigger and more complex, and as the security concerns grow, and the expected increase in flow of information through the cloud, the need for higher bandwidth, higher security, the ability to support larger numbers of nodes, and long-range communication becomes more and more apparent. Look at these forecasted numbers: 4 billion connected people, 25 billion applications, 50 billion connected devices in the next few years. The forecasted numbers are staggering, and it's across all industries, from consumer products to healthcare to transportation to retail to smart structures and more. So how do we address this huge market? For this, a new communication method needs to be envisioned and planned for. The communication method not only has to meet customers' application requirements, but also address the cost of implementation, time, and resources. This is especially true in larger smart city applications such as smart grids, building automation, street and public lighting, smart homes, security and surveillance, and many others, where a new network must be deployed to meet today's requirements. There are, of course, many options available to system integrators today, from installing highly complex wireless networks to very costly wireline installations, but none of them fully address what is actually needed. Today, I'll be talking about a wireline communication technology that not only addresses the requirements of today, but will take us for the next 20 years. So let me tell you how this all started. We were approached by several major customers in the building automation and industrial IoT sector in the past few years. And what they all told us was, while they're happy with their existing communication protocols such as LANWorks, BACnet, KNX, they are dissatisfied with the bandwidth limitations of the network itself. They felt it no longer supports the new requirements of IoT, things like data rate, security, range, number of nodes. Also, they had other concerns such as long-term availability, the solution's competitiveness, and the high cost of deployment. So they gave us a challenge and asked us to come up with a solution that addresses all these issues. So when we look at all the key system requirements, need for higher data rates, supporting more nodes, long-range communication, IP-based, high security, fast response times, and from an end application point of view, and when we are deciding which technology best fit today's requirements, the one technology that stands out is broadband PLC. That's closest in meeting all the requirements of the end customer, and that's the topic of today's webinar. The technology is called HDPLC. It's a broadband PLC technology developed to address the industrial and building automation markets, as well as certain consumer applications. It is based on IEEE 1901 standard, and we are proposing it to Landmark as a new channel standard for LAN. Today, we'll be giving you an overview of the technology and comparing it to some of the more popular technologies in use today, such as Ethernet and RS-485. So if you've been in this space for a while, you already know that existing communication technologies require difficult trade-offs. As an example, with serial, such as RS-485, you get longer ranges, but have to sacrifice data rate. Or wireless holds the promise of easier deployments, But range is an issue. Also, security is a concern. Of course, narrowband PLC offers the lowest deployment cost, but the narrowband solutions, you're limited with kilobit speeds, and it's not robust enough for a lot of the new applications. And then there is Ethernet. It is being tried by several companies, but the cost of installing new Cat5 wiring keeps many projects from getting off the ground. So Landmark and other industry leaders recognized all these challenges, and that's why they are supporting HDPLC as a new channel standard for high-speed wireline communications. Currently, Landmark and its members are proposing that to add HDPLC in IEC ISO as a new communication channel. Finally, you'll have a communication technology that provides the bandwidth, range, and many other capabilities required by modern smart systems, all using your existing wiring infrastructure and the same protocol stacks and tools that you already know and have used for many years, reducing the learning curve or having to invest in a new protocol or a complete system changeover. Our customers tell us this is a real game changer for them, enabling smarter, more secure applications, faster and cheaper deployments, and plenty of performance for future application requirements. So what's special about HDPLC? For starters, it gives you a big performance bump from kilobits to megabits. So you can send bigger packets more often, reaching more nodes in larger network configurations. You get the plug and play simplicity and IP-based mesh networking, and the strongest security at every node using AES 128 encryption engine. With HDPLC deployments, it's as easy as plugging in the device and turning them on. The rest is pretty much automatic. And the biggest benefit, if you get all of these capabilities without having to replace a single wire. So big performance advantages, lower deployment costs. It's a win-win for everyone, especially for your end customers. And how is this possible? So let me back up and review some of the key characteristics between various wireline technologies in use today. RS-485, narrowband PLC, broadband PLC, and Ethernet. The x-axis shows the operating frequency for some of the more popular wireline communication technologies, and the y-axis shows the relative range. So here, the lower the frequency band, the longer the transmission. As an example, RS-485 on this chart operates at a 9.6 kilohertz, having the longest range, versus Ethernet operating at above 125 megahertz with the shortest range. And PLC is in the middle of the road, operating between 2 to 100 megahertz, depending on the technology you are using. There are several broadband PLC standards in use today, developed for various applications. And there is Home Plug, developed for home networking, G.HN, for telecoms and last mile access, and HDPLC for industrial networks. There are a couple of unique features for HDPLC. One is the frequency band, and the other is its repeating functionality. We selected the frequency band between 2 to 28 megahertz for optimum cost performance. We found the higher frequencies above 28 megahertz doesn't really add much more performance, while it makes the chip architecture more complex and more expensive, and the power consumption goes up. The other unique feature is its repeating function. It extends the communication range comparable to those of low frequency and performance of those of high frequency. With HDPLC, you get the range of RS-485 and the performance of Ethernet. So here I want to talk to you about some of the challenges of communicating over power lines and some history. Companies nowadays shy away from PLC due to its history. The reason being that narrowband PLC historically has been slow and unreliable. So it didn't get the adoption and left a bad impression in people's minds. Even so, there are more than 200 million devices that have been deployed using PLC. And that's because of its inherent advantages that we touched on earlier. And that's the ability to reuse the existing wiring. But as with any emerging technology, PLC has made great strides in solving many of the issues narrowband PLC faced in the past. With HDPLC, we have solved the inherent problems of narrowband PLC. First of all, we operate in higher frequency bands where it's less noisy. And second, we operate over a wider bandwidth, which helps us apply more advanced communication techniques such as using OFDM modulation and forward error correction techniques to provide a more robust data communication in the presence of narrowband interferers, group relays, jammer signals, impulsive noise, and frequency selective interference. Here I have categorized PLC technology into two, legacy versus state-of-the-art. Now Matthias will talk about this in more details in his section of the presentation, so I won't spend a lot of time here. In general, the biggest difference among the legacy power line communication technology and the state-of-the-art is in their operating frequency, bandwidth, and modulation scheme. These are the main factors determining the degree of robustness, data rate, coverage, and range that can be achieved. There are also other areas of the technology we've improved, such as supporting IPv6, supporting higher number of nodes, higher security using AES-128, and so on. One of the biggest innovations in HDPLC is the use of a routing technique called CMSR, which stands for Centralized Matrix Source Routing. It's based on on ITU standard G9905. It was defined specifically for industrial networks where longer ranges, support for larger networks, and robust communication is required. It allows any node to act as a repeater. With this technique, you can extend the range of broadband PLC by 10 times to a few kilometers. Of course, range depends on many factors, so it's hard to be exact, but this can give you a good idea of its capability. We call this feature multi-hop. In addition, with this method, since the master handles all the transactions, we can drastically reduce the network traffic, allows having larger networks and faster connections. Some of our customers are seeing authentication times of less than 30 seconds for networks of 600 nodes and more from the time they turn on the system. The system continually monitors the lines and dynamically selects the best route to transmit the information to its destination. What we call automatic routing with dynamic self-optimization and self-healing feature. As an example, and as you can see in the figure, if you want to transmit packets from the master to, let's say, terminal 3, the system continually monitors all the lines and looks at different characteristics like the fire rate. And the algorithm does the channel estimation and calculates the link cost every so often for every node and determines which is the best route to reach terminal 3. And if the line conditions change, then it automatically changes the routing. We also added other features such as redundant master capability, where if one master fails, the system automatically changes over to another master. Again, the whole goal is to provide the most reliable, more robust communication throughout the network. And I think we have achieved that with HDPLC. The biggest advantage of HDPLC is using the existing wiring infrastructure that's already in place, whether it's the power lines or other types of wiring. It gives you the ability to communicate through the same wires that provides power to the device. Or you can use the existing control lines that's already in place, whether it's twisted pair, coax, Cat5, even telephone lines. The other advantage is the ability to bridge between various communication technologies and protocols, or use it as an extender. In addition to enabling various bridging functions, you can also do power over Ethernet or power over a coax. What this means is cutting out one of the major expenses in any project, and that's not having to pull new wiring. And it's protocol independent. Whether it's LAN, BACnet, KNX, or any other, HDPLC can transport it over any wiring. And lastly, it is free topology. You can connect your network in any configuration, whether it's bus, star, mesh, tree, HDPLC supports it all. Here are the key specs for HDPLC. First, it is based on an internationally accepted IEEE 1901 standard. It uses many of the same schemes as Wi-Fi and other advanced high-speed communication technologies such as OFDM, which allows a more efficient use of the frequency band, thus allowing us to add more advanced forward error correction schemes, such as convolutional coding, read-summing, to achieve more robust transmission, provide higher speeds, lower latencies, security, as well as IP communication. Also, HDPLC is supported by many internationally recognized organizations, and interoperability and certification is done by the HDPLC Alliance, as well as the upcoming Landmark International. Again, Matthias will talk about that a little later in his presentation. To review, the technology we are presenting today meets all the requirements we talked about earlier for today's smart city and more. HDPLC addresses the higher data rates. The throughput is more than 90 megabits per second, supports more nodes, up to 1024 per each line, offers wider range, more than a couple of kilometers. It is IP-based. It supports IPv4 and IPv6. It offers a strong encryption engine based on AES-128 for the highest security at every node, fast response times that are in milliseconds, and it's standards-based. It is available through multiple vendors, and its interoperability and certification process is in place to assure competitiveness and availability. And best of all, it offers the lowest deployment cost. So we feel we've achieved all we were asked by our customers and met the challenge. Now we hope you take advantage of this standard and use it in your next projects. These are some of the applications that can take advantage of this technology. I can confidently say that the majority of the wired applications in use today use some sort of serial communication, such as RS-485. There's also a large number of installations that use narrowband PLC. And there are those newer systems that are now using Ethernet. And lastly, some low-speed wireless is being considered. When we compare all these technologies, we see none of them fully meet today's building automation requirements except HDPLC. We believe HDPLC is a good option for the home and building automation, as well as smart city applications such as smart grids, smart streets, and public lighting, smart factories, smart transportation, security and surveillance, and many more. It provides the required data rates, security, range, robustness that one would expect from their communication network. We offer a fully integrated low-power IC that's fully compliant with IEEE 1901 with all the features I just described. It offers a low-cost solution in a small form factor. The solution comes in two versions, one designed for speed and the other for range. The evaluation kit includes all the hardware, software, and documentation to easily set up and evaluate the performance of the system under various conditions and configurations. And we offer various reference designs to qualified customers, including schematics, layout, and best supporting possible to make the design much faster and easier. The software development kit provides the source code and documentation and tools in case customers want to run their own application on the chip. We also provide a comprehensive set of tools for design, implementation, and test of large networks. The PLC Network Manager software helps customers configure, monitor, and manage complex networks. With this tool, you can monitor and the communication quality of each node, look at the network configuration by topology, and be able to quickly identify and troubleshoot problem areas. The tool comes standard with our SDK. These chips are available today for your evaluation and design consideration. This concludes my portion of the presentation today. I just wanted to remind you to please visit our webpage. There is a wealth of information there to help you make a better decision when it comes to communications and networking. I would like to thank you again for your time and interest, and thanks to Mike McKenna and the Engenuity team for arranging this webinar. I now would like to hand the presentation over to Matthias from Gesitech. We have been working with Gesitech for the past 2 years on this effort, along with many other Landmark members, such as Engenuity, to bring this technology in the hands of the customers. He will talk about some of the progress and products they have in the pipeline. Thank you.
Okay, thanks, Michael. Thanks, Mike. It seems I'm already the presenter. Hopefully, Mike, you can confirm that you see my screen too.
We've got you, Matthias.
Okay, so in the second half of the webinar, I want to show some more details about how to work with HDPLC and LON in combination. So a little bit about my person. I'm a LONWorks specialist since 1995, so at least more than 20 years. I'm the Chief Technical Officer at Gesitech. Since a few years, I'm in the Landmark International Board and in the Landmark Germany Board. I'm working there in a couple of task groups like the Standard Channel Committee, which is actually working on the standardization of using HDPLC together with LON, and in other industrial committees, for instance, in Europe for petrol stations, in the German Dean to access the standardization committees we have here in Europe. Europe is the keyword. The company Gesitech is located in Germany. Most likely you will recognize my accent. The company is pretty small, having 15 employees, but we are doing worldwide business and we are doing LON business since the very beginning of LONWorks. We are a technology-related company, of course, working with Linux, Windows, and other embedded operating systems. And our main business is LON interfaces, routers, other LON infrastructure components, not that much intelligent controllers. And since more than 10 years, we are owning an own LON protocol stack, and we are producing for the standard wired LON topologies like free topology or twisted PAXF. We are producing our own silicon based on VHDL. So that makes us very competent LON developer company compared with others all over the world. So I want to tell a little bit about the technical facts, going deeper into the details. Michael already showed what is exactly HDPLC LON and how does that interoperate with LONWorks. Then we are going to the technical solution we are using together in companion with Megachips PowerLine chip, a standard Cortex CPU. So this complete independent LON solution without a neuron chip, without neuron C. I show something about the HDPLC LON evaluation kit we are selling through Engenuity, and I show a little bit practical in a kind of virtual hands-on. I have some equipment here on my desk, and you will see later how this is working with all of the different LONWorks tools. Here it is a little bit more detailed compared with Michael's slide. You have already recognized the narrowband PLC, which is limited to low fire rates, especially. I added a column for the well-known Echelon power line, which is a narrowband power line communication too. So it is working in 2 frequency ranges, dependent on the location of the Earth. So regulations are different in the US and in Europe. But at least you need to recognize that the legacy power line communication we have in LON is pretty slow. It owns error correction, but at least the number of nodes is limited by the environment. So there is a practical maximum number of nodes due to the low transfer speed, and of course related to the physical dimensions of a network. So we are superseding that with a broadband PLC based on HDPLC, which makes us much faster compared with the old narrowband powerline communication technologies. And what is new additionally is we are IP enabled. If it is IPv4 or IPv6, the devices are now IP enabled, generically IP enabled. The Megachips CPU is having Ethernet on board, on chip, so that makes each HDPLC nodes capable to use Ethernet as a second communication port. And you have to keep that in mind because that's interesting for a couple of applications. Again, here I have to compare that with RS-485, with HDPLC and Ethernet. While the maximum number of nodes in an Ethernet is more or less dependent on the number of switches, and this is what Michael already told you, that the cost of infrastructure in an Ethernet-based industrial control network is pretty high. In RS-485, the maximum distance is at least 1 kilometer. The speed is limited and so on, and there is no flexible topology. And at least all people working with RS-485 know that there is one nightmare, and this is grounding of the communication line. And all of that is vanishing using HDPLC. So how do we connect LON and HDPLC? Well, HDPLC becomes, with the work we are doing in LONMARK and the standardization committees, becomes just a new physical channel for LON. So it is comparable to a TP-FT10, to a LON TP-XF1250, or comparable to a LON over IP. So it's a new physical LON channel only. It is not compatible with our existing powerline channel in 709.3, but it can coexist on the same wire. We have the standardization procedure started already last year. We are doing that in parallel in the US with ANSI CTA and in Europe with CEN. In the US, we will finish a little bit earlier because ANSI CTA is more productive compared with the European standardization bodies. So I expect that 709.8 will be finished end of 2018, and in Europe we will target that for mid-2019. If you have a LAN device for HDPLC, you can have additionally Ethernet available on that device, so that a LAN HDPLC device can have double functionality, like it is a control node or a router, for instance, and in parallel it gives access for other devices, Ethernet access to central infrastructure, like adding CCTV, like adding sensor gateways, like adding audio. If you think of street lighting using HDPLC LAN to control the electronic ballast, you can additionally hook up a CCTV camera to control the street using this electronic ballast if it has the RJ45 output, and it is using the same power line channel, the same HDPLC power line channel compared where we are having HDPLC LAN running. We did that in intensive tests in the labs that we ran in parallel HDPLC LAN and full HD video camera, and they don't interfere with each other. And the LAN traffic is overall only is using a minimum of bandwidth of the HDPLC capabilities. So we have devices like the Megachips KHLN1501 CPU, which is running our LAN protocol stack. We will have GiziTech HDPLC modules. There is a LAN HDPLC transceiver for the Neuron 6000. And additionally, we are coming up with a lot of diagnostic tools. There is a topology analysis. You can see the signal strength. You can do performance updates. You can do a firmware update. And all of this functionality is integrated already in the power line chip. So there is no need for a special device. You can hook up your laptop, connect with Ethernet to the power line controller, and run the diagnostic software from Megachips, and then you can see what's going on in the network. You can see the topology, and you can update the devices, for instance. So what is the stacking of the different standards? We have the IEEE 1901, which is defining the OFDM modulation. On top of that, we are adding the multi-hop standard, ITU G9905, which is defining the interoperability between different power line standards and the multi-hopping, HDPLC, how to use all of that. And then on top, we are adding LANWorks as an IP-based protocol with our well-known standard data types, the snippets, the object models, the standard functional profiles. In the table on the right side, you see a little bit more, 2 columns more, 2 rows more, like the latency. We have a latency of about 20 milliseconds. We have seen more than 200 packets per second throughput in a network. And I added another security feature that we can have a whitelist of devices that makes the device, that makes the HDPLC network more secure compared with other networks where you can just hook up a node and you are in. So this is the Megachips GiziTech solution for an HDPLC LAN device. You have the powerline CPU, which is running a generic LAN stack. It is having a Neuron ID. and that makes the HDPLC CPU a real LON device, which is, according to the 4908 standard, fully compliant to all of the standards we have in LON. This is connected with a serial line to a small Cortex M0 CPU, which is pretty cheap, and this is just running a tiny application to drive the GPIOs. Normally, the needs you have in your target application, like maybe an electronic ballast for an LED lighting, requires pulse width modulation, analog inputs and outputs, and so on. So it's a wise decision to choose that CPU dependent on the needs you have in your application, or you already have specific know-how, or you have an existing design with a CPU architecture and you can reuse that existing code. In our module, we add 12 digital input outputs. We add 4 analogs, 2 analog inputs, 2 analog outputs, and some debugging. Of course, there is a debug UART output. And all of that is connected to a baseboard with power line and Ethernet to show, to connect on the one half to the power line network, on the other half potentially to another Ethernet device. So we have chosen the Cortex M0 as one of the most cheapest CPU architectures available. This is a chip something about $1. It comes up with a standard NZC environment, which is a little bit more suitable for the newbies we get now from the universities and are starting with programming. So overall, this is a solution without a neuron chip. It is using our EasyTech EasyLearn protocol stack, which is inside of our devices since more than 10 years and sold something about with more than 100,000 devices up to now. We are selling an evaluation kit, which is based on the standard Megachips Dolphin evaluation kit. We extend that with a module we have with this GPIOs. So you see here the table we have. So it's 12 GPIOs, programmable, digital, including possibilities to have I2C, SPI, UARTs, and other serial data models. It contains the debug pins for the ARM debug, which is inside of for the Cortex M0, the digital, the analog inputs and outputs. And what my colleagues from the software department all the time like is having a diagnostic UART to show something what is going on. So if you want to develop a LONWorks node, we normally have to consider in the very beginning what behavior, what functionality shall this LONWorks device have. And this is now the situation where LONMARK jumps in. In LONMARK, we are providing the definitions for data types and for functional profiles. And we are collecting that in a file which is called external interface file, the XIF. LONWorks developers know that. For non-LONWorks developers, it is a kind of electronic data sheet describing the functionality of a device, including all the data types, the different items you can communicate with can have. So we additionally, we have configuration properties, so like PID controller parameters or something like that. The definitions inside of this external interface file is what a node makes interoperable. So I know Ernst Eder, our technical director of LONMARK, is in that call. So, you know, the first thing, if a node needs to be certified is checking that XIF, if this is following all the rules. So if we are using a third-party silicon to make a LON device, we need to have some tools to make the development flow easy. EasyTech is having a XIF generator, so you can set up, you can define that external interface file with a Windows application, and this is generating an NZC framework, including the network variable definitions, the functional blocks, having callback events from the communication library. So it is generating already an NZC framework. You can drop it into the node, and then it already behaves like a LON node, of course, without GPIO functionality. So the next step is connect the GPIOs with the network variables using the callback events. Test it using the ST-Link debugger, download, fix bug, and fixing bugs and all of that. And at the end of the day, you will be ready with your application. We are right now working on an outdoor street lighting controller. That is the reason why you see that XIF, especially from the Asian market, we have a lot of requests for this kind of development. This is what you get. You get 2 of the EVK boxes together with a breakout board, all the cables you need. You get an ST-Link debugger. You get a USB dongle for some EasyTech licensed software running on the PC. And Michael already told you that we do have an HDPLC master device checking the topology of the network. And we took a third-party device playing the role of the HDPLC master and the HDPLC LON master functionality. And it tells you additionally that HDPLC is interoperable because we are mixing different vendors in our evaluation kit. And we are adding all the power cables you need for Europe and for the US. So this is what you have inside. It's just a reminder for what I told you. And you get all of the software you need from an FTP repository we have set up for you individually. You need to have something additionally, of course. You don't get a PC from EasyTech. So you have to provide a PC for the setup, and my recommendation is use a PC with a second Ethernet interface. It makes working with the EVK much simpler. To work with the STM Micro Cortex M0 CPU, you can use Atomic True Studio, which is downloadable for free. The GPIOs are defined using STM32CubeMX, again, which is available for free. To test bindings, so the connections, the LON connections between the 2 boxes, you need to have the ISOT configuration tool from Echelon. You can have that in a 30 days limited trial edition. You can download it from the Echelon website, request a trial key, and then you can work with that. Or you have that already. And at least if you want to have a look at the debug output, you need any UART-enabled terminal application. So this is the setup I have on my desk right now. All of the software is running. And now I want to switch over to my camera that you can see what I have here available on my desk. You see the same. So this is the first one, the second one, the debugger, all of that connected is to a small power strip. I recommend to use a power strip that makes it easier to turn on and off power for that. So keep in mind, we are working with 110 volt or 230 volt. So there's a little bit of danger in that. The kit already comes with a preloaded application. We do have a push button here on that board. There is an, oh, I have to turn it on, sorry. There's an LED side by side. Yeah, ready now. So I can control the LED by the push button on the other module, vice versa. And this is already LAN communication. So let's see a little bit more how that works. The first thing I have to show is, not this one, is the blue chip network manager from Megachips. It tells me that I have here this infrastructure on my desk, a master and 2 terminal devices. The terminal devices are the evaluation kit boxes, and I already can see the topology, which is quite simple. This is the master, these are the terminals, and right now we do have 168 or 169 megabits per second communication speed between the boxes. I do have a couple of LANWorks drivers accessing that network. It makes working with that easier. More details you find in the documentation. And the first one I like to do is just starting NodeUtil. On that, I think most LAN engineers are familiar with NodeUtil. I can press the service pin push button on that, and then I get here via power line my service pin messages into NodeUtil. I can list the network variables, so everything behaves like you know from a standard LAN device. I can pull the variables, so everything is behaving like we know. The last time, the first time we had been working with that, we didn't cover, I think, LAN scanner. So additionally, I need to have a network. So here I'm using Echelon's protocol analyzer, which is connected to the board. So I can send, again, service pin push buttons. I can pull the network variables, and you see the standard traffic here inside of a standard LAN protocol analyzer. And so there's nothing different compared with other LAN nodes, like a TP-FT10 LAN node. You see the same utilities are running without any tricks or tweaks. So next thing I have to show is now using the XIF editor. A lot of that is prepared, so it shows me the name, the program ID, the self-identification. I do have a list of network variables. So for instance, for the digital outputs, I made an NVI digital with an array size of 6. So I mixed my 12 digital IOs into 12 inputs, 12 outputs. Here we have the outputs, analog output, analog input, and at least a tiny one is the NVO CPU temperature, because that tiny little chip contains already a CPU thermometer. And the only thing I have to do is export that for our EasyLearn protocol stack. More explanation for that you find in the documentation. And then it is done. Let me change to the editor. That's one. So now it generated a header file, which is including the definitions for the maximum number of arrays, how many memory we need, the self documentation, the application ID, a definition for the NV indices, and a few of the functions we have running. The other one is the definition for the inputs and outputs with a default value already with the types. 95 is the snippet switch. Some people know 105 is a snippet 10p. So we generate already a framework which is running most of that what you need. There is a callback functionality if there is an update from externally, which is with a large switch case, giving you the opportunity to hook up own code. When I have a look into my source code, don't be concerned. Most of that is generated by a utility from ST itself. You see here user code begin. So the only thing I have to do is I'm initializing here my debug UART. I'm initializing my EasyLearn protocol stack. And then I have a merry-go-round function for the protocol stack task function. So we are running in a bare metal environment without any operating system. And this is the opportunity to make HDPLC nodes small and cheap. When I have a look how into the, let's go here. When we now have a look into the filled-in, just having a look here what's happening with now when one of the digital NVR digital network variables is triggered. I just write down that to the given ports of the STM micro. So this is all what I'm doing. Last but not least, I have to show that with LearnMaker for Windows. Open LNSCT. Where's Open LNSCT? Oh, yes. Oops. That's wrong. I'm working with Unity. Sorry. Yeah, that was the situation we had the last time too. That okay, marvelous. So here we are. This is this is my network. So I have two of my boxes here. These are the functional blocks. Now I can make it larger again. You see I have my NVI analog, my NVO analog, the digital controls, and this is the binding I made from the push button to an LED and vice versa from the other module, from the push button to the LED. I'm able normally to browse that. So you recognize now, let me see, it's the correct one. I'm pressing the push button here. You see that there's something going on. I made a connection from between the analog inputs and analog outputs. There's a small piece on wire showing that. So again, you see it is working like a standard Lonworks node. And this is what I wanted to show with that virtual hands-on. I have a few slides at the end, just to confirm that we learned everything I wanted to teach you. So what are the devices we are working on? At first, we are making a DIN rail gateway from HDPLC to Ethernet and RS485. Based on that, we will have a Lonworks router from HDPLC to TP-FT10 or other existing Lonworks physical channels. There will be an intelligent power plug for retrofit energy management, and you are able to turn on and off DGC devices using HDPLC and LON and any other intelligent I/O device. Be excited for the AHR Expo in Dallas, beginning of next year. We will be there on the Lonmark booth, and you will see the first devices run. So what did we learn? HDPLC is really standard LON. We can control it with all standard tools like LONmaker, third-party utilities, and it is additionally communicating with existing LON networks. So if I add a router, I can communicate from a TP-FT10 node to an HDPLC LON node. NZC is making the development easy. You can migrate existing know-how from other CPU platforms without using a neuron chip. And people knowing short stack from Echelon will have recognized that it is a comparable solution. We have separated the application and the LON stack on different CPUs to make all of that very robust. So the LON stack is running on the HDPLC, making it a robust solution. The end user's application cannot interfere with that stack, making it corrupt. So we are a little bit over time. Unfortunately, let's go here. So Mike is your contact in the US to get more information, to get quotes, to buy the EVK. And I think we are now open for, if there's time left, we are open for question and answer.
I think I've addressed most of the questions. So if anybody else has any additional questions, now is your chance to raise your hand and we'll get those addressed. Okay, great. I just wanted to say thank you to everybody for joining. Thank you to Michael and Matthias. And we will be uploading this to our website and YouTube channel and sending it out for everyone. Have a great day, guys. Thank you. Bye-bye.